So now here's one for you to do. For y equals x squared, same function, but now we're going to go to a equals 3. What is the slope of the tangent? What is the equation of the tangent line? Review the last video if you need to, and try to do that on your own. Pause the video and try to do it on your own right now. Go! All right, I'm assuming that you have now paused the video, done this equation, and come back. And I hope that you found that the slope of the tangent was equal to 6, and that the equation, the point of tangency was 3, 9. That's your a, f of a. And so you got the equation y minus 9 equals 6 times x minus 3, or y equals 6x minus 9. All right, and then so if you got that, if you didn't get that, let me know, or just go over the videos again. Let's go ahead and look at that third point of tangency, line of tangency, right? So here's our 3 lines of tangency. All right, here we are, tangent at x equals 1, that's this line. Tangent at x equals 2, that's this line. Tangent at x equals 3, that's this line. All right, so that's what tangents look like, and you can see how they sort of trace out the overall shape of the graph. I don't know if there's a zoom that will show that better somehow. Maybe. Like that is pretty good. All right. See how the tangents are sort of tracing along the shape of the graph? There's some interesting applications of just that in itself. But that's not really our primary concern. So here's what we're going to be interested in right now. It is good to look for and notice patterns. So when we had a and we had the slope of the tangent at a, when a was 2, the slope, well, sorry, let's start with a is 1, the slope of the tangent was 2. A was 2, the slope of the tangent was 4. When a is 3, the slope of the tangent was 6. Now all of this is contingent on the fact that the function we're dealing with is y equals x squared. A different function would give you a different relationship. But clearly there's a relationship right here. It looks like the slope of the tangent at a is equal to just 2a. So it's good to be able to look for and notice patterns, but noticing a pattern doesn't mean that that pattern is 100% strictly valid. So what we're going to do now is actually prove that there's a reason for that pattern. Okay, so the way that we're going to do that, besides wrinkling up our pages, is, so let's say we don't specify a. So we're just going to find the slope of the tangent for any a. And so we'll just call it x instead of a to emphasize that it's not a constant. We're going to look at any value on the x-axis. All right, but we're still dealing with y equals x squared. That's our function. Okay, so here's how we could do that. We could do the same things you just did. The slope of the tangent is equal to, so it's the limit as h approaches 0. Let's see, how did we specify this originally? F of a plus h minus f of a over h. Okay, but now we're not going to specify what the a is. We're just going to leave the a being x. All right, so we're going to look, so we're not going to plug in values for a. So we're going to do limit as h approaches 0, f of x plus h minus f of x over h. So for this particular function, y equals x squared, so for our f of x equals x squared. All right, so that means that we can say that this equals x plus h squared minus x squared over h, right? Just leaving these values as x. Then we can just do the algebra on that. So I'm going to have x squared plus 2xh plus h squared. That's just this squaring out this binomial. And then I have minus x squared. And then that's over h. All right, so that is equal to the limit as h approaches 0 of the x squareds cancel. I have 2xh plus h squared over h. I have a limit, so I can reduce the h's. So I have limit as h approaches 0 of 2x plus h. Now I can sub the value h equals 0. The x I'm just going to leave. Because I'm substituting and evaluating the limit, I drop the limit sign, 2x plus 0, 2x. So now I know, in fact, that for the function y equals x squared, no matter what the value of x is where I want to find the slope of the tangent, that slope of the tangent is always going to be 2 times the x coordinate. This is an extremely powerful result, and we're going to look at this right here a lot. So this has a name. It is called f prime of x. And this is a definition of f prime of x. It's the instantaneous slope, or the slope of the tangent, to a function f at any point x. So it is called the derivative of f. It's f prime of x. This is the definition of the derivative, the limit definition of the derivative. This concept is important and shows up in many different contexts, and therefore it is written many different ways, such as dy dx, that's one of them, and capital D subscript x, f of x, written the derivative with respect to x of f of x. This you just say dy dx. So when you see this in calculus, don't say dy over dx. We just say dy dx. Now, a couple of words about these notations. This formulation dy dx comes from the fact that we're really looking at the limit as delta x approaches 0 of delta y over delta x, right? y2 minus y1, that's what delta y is, over x2 minus x1, that's what delta x is. When we take the limit as delta x approaches 0, then we call that dy dx. So dy is like a limit of delta y, dx is like a limit of delta x. All right, and this one, dx f of x, is read the derivative of f of x with respect to x. So the with respect to x means x is the variable in the problem. So this is going to be kind of somewhat implicit in a lot of the work we do in this class, but when you get a multivariate calculus, and actually some of the problems we do in this class, like implicit differentiation, it's going to be important to know with respect to which variable you are taking the derivative. In other words, what is the variable that you're adding h to? There will be cases when that will be y. All right. The limit definition of the derivative. This is one of the most central and important things you will ever learn in calculus. Anyone who wants to call themselves a calculus student has this memorized. They know this by heart. Again, I don't like the word memorize. I like know. I like understand. You need to know and understand this definition in order to claim that you know anything about calculus. And now you can do that. See? Okay, more examples coming.